using this power rule, and let's think about if we need any other like exceptions, or this is what we'll do for the rule. So as a formula, if you have x to the n power, the formula can be this d over dx means that you're taking the derivative of x to the n power. So if n is a number, we would multiply out front by the number, so that n is written out here, and then in the exponent there we would need to subtract 1 from our n. Okay, is that the rule you guys were using? Does that make sense how it could be represented in a formula there? Whatever the exponent was gets multiplied out front, and then you subtract 1 from the exponent. If you wanted to update this rule a little bit, you could put another constant out here, like if there's a b or something here, you could make it, in fact, let's write that. You could make it, like maybe you're taking the derivative of like b times x to the n power. Well, if you did that, you would multiply out front by the n. You'd have n times b x to the n minus 1 power, right? So there could already be a number out front. So it makes it super fast to take the derivative. Like for example 1, where we would have had to do this big long limit definition of a derivative, now we can just do f prime of x equals 3x squared for that. Just multiply out front by the 3, subtract 1 from the 3 to get 2. If you have a number already out there, that's fine. You just multiply by that number. So you're going to do 4 times 5, which is going to give you 20. And then you'll do x to the 5 minus 1 is going to give you 4 right there. Okay. So that power rule, as soon as, like, when Hunter was in, like, 4th grade, one afternoon, I taught him how to do this. He had no idea what he was doing, but he could add, subtract, and multiply, so he could do it. He could get the right answer on these. So this is going to be very straightforward, but there's going to be some circumstances that make it a little bit trickier. So let's talk about that. Now this is written as a separate rule. It's called the constant rule, but I would argue that it's not all that necessary. If we have a function like this, f of x equals some constant, let's just use a number like 7. Okay? I would argue that our other rule applies anyway. I do not have an x here, but if I did put an x here, what would the exponent have to be? It'd have to be 0, right? For it to equal 7, right? Okay, so let's apply our rule. If I take my exponent, I'm going to multiply it by the number out front. That will give me 0. And then what we'll have to do to my exponent? Subtract 1. But what is 0 times x to the negative 1 power? It is 0. So the derivative of a constant is just going to give us 0. In reality, it's just an application of the power rule anyway. Because there's 0 x's there, x to the 0 power would just equal 1. So yeah, because this was just 7, right? Now, a difference would be like, let's say we had, let's use a different letter there, g of x equals, let's say we had 7x. Now, this is a different equation, right? What's the exponent on that x? 1. So, again, power rule still applies. When you take the derivative, 1 times 7 is 7. Sorry. I think they're just calling to remind me of Henry's appointment, which is tomorrow, but then it makes me worry that it's actually today. Surely it's tomorrow. That's what I've made plans for. It's got to be. All right. And then so I would have x, and then I have to subtract 1 from my exponent, which would be 0, right? But x to the 0 is just 1, so I just get 7 when I take that derivative.
Couldn't you also just multiply the exponent still by the number in front and be 0 to the 7 and then 0? Like how we were doing earlier.
Yeah. properties of derivatives, if you have a scalar multiple, if you're like a number that's multiplied out front, it just kind of stays out there and you multiply it. If you have things that are separated by plus or minus signs, you just take the derivative of them separately. So if you have like 6x to the third plus 7x squared plus 4x, you just take the derivative of each little piece separately. If we look at some examples here, these first two are pretty straightforward. So for this first one, Emma, what would you get for the derivative of number 1? Okay, right, very good. Derivative of that negative 1 is just 0, so it goes away. And this is your derivative, right? Let's see. How about Ethan? What's your derivative of number 2?
45x to the 4th minus 6x squared plus 6.
Okay, beautiful, right? Looks great. Now, when we get down to 3 and 4, we start to run into some problems. Because that has a fraction. Nothing about the rule said anything to do about a fraction. You might be tempted to say it is 1 over 5x to the 4th. You cannot do that. That would not be it. If you get a fraction or a root, you have to write it as just a x to a power first. So this right now is in the denominator of a fraction. How can I move it back up to the top of a fraction? Negative exponent. So it would be acceptable to write this as x to the 5th. It would not, negative 5th, right? Okay, so that is not taking the derivative. That's just rewriting this so that we can take the derivative. So if I want to take the derivative of this, first of all, they used a y instead of a f of x or a g of x. There are a couple different acceptable ways to do this. If you have a y, you can use a y with a prime behind it, or you can do dy over dx. Both of those expressions are going to denote that you took the derivative of the y there. So you could use either one. You don't need them both there. You could use either one. But if I use my power rule here, I'm going to multiply out front by my negative 5, and I'll get x raised to what power? Negative 6. Not negative 4. I always do that wrong. I take away 1 from the magnitude, not 1 from the actual value, but negative 5 minus 1 is going to give us negative 6 right there. You can leave it like this. Sometimes they will do this. They'll make it negative 5 over x to the 6th power. They'll move that x back down to the denominator. What I would like for you guys to do, the problems that you get that in the book that are odd, check the back of the book to make sure you're able to make it match what they have in the back of the book. So either one of these are correct, but just try to get it to match what's in the back of the book. How can I rewrite number 4? How do I rewrite radicals so that it's x to a power? It's a fraction. Yep. Fractional exponents. What would it be for this one? It's 1/3. So whatever your exponent on the inside is goes on top. The root goes on the bottom. Okay, so if I want to take the derivative of this, f prime of x, I'll multiply out front by 1/3. I got x to the what power? Not negative 4/3. You're doing 1/3 minus 1. Yeah, if it was a negative 1/3, then it would be negative 4/3. But you're doing 1/3 minus 1. You got to get common denominators. So you got to multiply by 3 on top and bottom here. That is going to give you 1/3 minus 3/3. And that is going to be negative 2/3. So you got a exponent of negative 2/3. Now, they might leave the answer like this, which is fine. They also may take this, that x right there right now is in like the numerator. You can think of these like being multiplied together here. It's in the numerator, so they might send it back down to the denominator since it has a negative exponent like this, and they might write it like this, 1 over 3x to the 2/3. They may even change that 2/3 back to a root, which in this case would be the cube root of x squared. So any of those things are acceptable as the answers. If it's a free response, just stop as soon as you leave the negative exponents. There's no like benefit in simplifying that. But for multiple choice, they could give any of those. And I would say like AP always leaves the answer this way, but it's not true. Sometimes their answer choices have negative exponents. Sometimes their answer choices have been sent back down to the denominator. Sometimes they turn them back into roots. You just have to be able to do all of the ways they might give it to you. All right, questions there? All right. All right, so let's just look at a few different ways they might like ask. It says find the slope of the graph of f of x equals 3x to the third minus 4x squared at these particular points. How do we find the slope of a graph? Derivative is the slope of the graph. So they're not asking you to find derivative, but this is what they mean whenever they say this. So if we take the derivative, Xander, what will we get for the derivative of number 5? Okay, now that is just our like general derivative, but if we want to know the slope of the graph at a specific point, then we just need to plug that number into our derivative, right? So make sure when you do this that you label it. So for A, I would say f prime of 1, and then I would just plug in 9 times 1 squared minus 8 times 1. That's just 9 minus 8, which is going to give us 1. So at x equals 1, the slope of f of x would be 1. For 0, I would just label it f prime of 0, and I will get 9 times 0 squared minus 8 times 0, and that will give me 0. And for the last one, f prime of negative 2, I will get 9 times negative 2 squared minus 8 times negative 2. What do I have to do first there? Exponent. So I'm going to square that first. I'm going to get 9 times 4 minus 8 times negative 2. Then I can multiply. So I'll get 36 plus 16. And then that is going to give me 52. For that. Okay, questions? All right, equation of a tangent line is going to be so much easier now that we have the power rules. So much easier because the derivative part becomes very simple, right? So when it asks you for the equation of a line tangent, there's 3 things you need to have. You need to find the point, the slope, and the equation of the tangent line. To find the point, what do we do? Plug the 1 into the original, right? So f of 1. Make sure you label that so it's clear what you're plugging into. And you'll have 1 over 1 squared. And what is that going to give you? 1. So the coordinates of our point would be 1, 1, because we plugged in 1 for our x. We got 1 out for our y. That's our point right there. To find our slope, we need to take the derivative. So right now, I've got f of x equals 1 over x squared, but I cannot take the derivative of that with the tools that I have right now. I need to rewrite this so it's just x to a power. What's it going to be? X to what power? Negative 2. All right. So the first thing I want to do is find my derivative, and then I'll worry about plugging in the 1. So I'm going to label this f prime of x, not f prime of 1, because I'm not plugging 1 in yet. And so when I take the derivative, I'm going to multiply out front by -2. I'll have my x. I need to subtract 1 from my exponent. What's that going to give me? -3. It's okay to leave it as negative exponents, but I find it difficult to plug numbers in if I have negative exponents, because I don't just like know those off the top of my head. You're plugging in 1, so it's pretty easy here. But I would move this back down to the bottom and make it -2 over x to the 3rd. So that's our derivative. We want to know the derivative at 1, so we're going to plug in 1. So -2 over 1 cubed is just going to give us -2. This is our slope right here. And then we just need the equation of our tangent line. And for that, we just use that y equals m times x minus x1 plus y1 that we have. So we got y equals, my slope is -2, x minus 1 plus 1. And that would be my answer. There. Okay. Questions? All right, let's look at one question that's sort of like an application problem. It might have been COVID. Whenever you guys had Miss Ball in the 8th grade, did you guys get to do the pumpkin chunking and make the catapults and do that? Did she have you do any of those problems? Yeah. It's in Math 1, I always try to do it. I did not get to do it with one class because of COVID. But every other year I always try to do it, even though I don't have Math 1 anymore, so I haven't got to do it in a few years. But whenever you have something thrown up into the air, it is going to behave in like a parabolic fashion, right? The height is going to be parabolic. So if I have a pumpkin is launched from a height of 15 feet with an initial upward velocity of 60 feet, this is the equation that we use for the pumpkin chunking in Math 1. The height is going to equal -16 time squared plus v sub 0 times time plus h sub 0, where v sub 0 here is your initial upward velocity and your h sub 0 is your initial height. So if we write this equation for this specific situation, I'm actually going to call it h of t. I like that a little better. It's going to be -16 t squared plus our initial upward velocity would be 60, so we'd have 60t, and then our initial height would be 15. So this is the type of equation we would have came up with in Math 1 when we were doing those pumpkin chunking problems. And we had some formulas and some different things that we used to analyze those quadratics. We also used Desmos a lot just to graph it. Calculus, like physics, you can approach physics from like a algebraic standpoint where they just give you a bunch of formulas. So many formulas. Did you take algebra-based physics? Yeah. Yeah, like all kind, like you have pages of equations, and they don't define anything. And every time anybody asks me for help on that, I get confused. So you can approach physics from a algebraic standpoint, but to me it makes so much more sense when you look at it from a calculus standpoint, because all of this stuff is related. So this first part is not really a calculus problem. It says what's the average rate of speed of the pumpkin from 0 to 1. So when we're looking at average rate of speed, we're just doing like slope between the points, right? So if I did h of 0, I would get -16 times 0 squared plus 60 times 0 plus 15, which would just give me 15, and that would be the point 0, 15. And if I plugged in 1, I would get negative 16 times 1 squared plus 60 times 1 plus 15, and that is going to give me 59. And so that would be the point 159. Okay, so if I want average rate of speed, I just need to know like how far it traveled over that 1 second, right? So it started off at 15 feet, and then by 1 second it was at 59 feet. And if I want to know average rate of speed, I just do the slope formula. So I would do 59 minus 15 over 1 minus 0, and that is going to give me 44 over 1, so 44, and this would be our distance is measured in feet, and our time is measured in seconds, so it'd be feet per second. Now, that's your average rate of speed. But whenever, like if you shoot something up into the air, as soon as it leaves the barrel of the cannon that it's launched out of, or leaves the arm of the catapult, gravity starts to take effect, right? And so as it's going up, it's slowing down till it gets to the very top. It is going to, like, for an instant, stop, and then it starts going back down, all right? So at this point, you got an average speed of 44, but that's not its instantaneous speed, right? So our instantaneous speed is our slope of our tangent line, right? So if we think about what the graph of this looks like, if I want instantaneous speed, it's the slope of that tangent line, which up until now we had to do limit definition of a derivative for, but now we have a much easier rule that we can use. So if I'm asked for what was the instantaneous velocity of the pumpkin at t equals 1, instantaneous velocity is going to be that slope of the tangent line. It is your derivative of the height. So if we find h prime of t here, we are just going to have we got to do 2 times negative 16, so we'll get negative 32 t to the first power plus 60. And we specifically want to know at 1, so h prime of 1 is going to give us negative 32 times 1 plus 60, and that's just going to be negative 32 plus 60, which is going to give us 28 feet per second. You're taking the derivative of your height function. So 2 times negative 6. Yeah. We didn't take the derivative of it earlier. We just like plugged in our numbers. Yeah. Okay. So it started off at an initial velocity of 60 feet per second. It was going faster whenever it was shot, right? And then it's going to slow down. So even though, like, between 0 and 1, your average velocity is 44, at 1, it's now only going 28 feet per second. Okay? And for the last one, it wants to know the velocity of the pumpkin when it hit the ground. So this is going to require some of the things that we learned from pre-cal and before. So, like, we're looking at a graph that looks something like this. It is going to hit the ground over here, right? How am I going to find when it hits the ground? We're going to see where the y value equals 0, your h of t equals 0 here, right? So if I take my height equation, not the derivative, derivative has to do with velocity. So if I take the height equation, that negative 16 t squared plus 60 t plus 15, I want to see when it equals 0, because if the height equals 0, I have hit the ground, right? Now, how are we going to, I think we're probably going to need the calculator here. We can do it by hand, but I think we're going to get decimal for this answer. So you could graph it. If I had to do it on the calculator, I probably wouldn't graph it. I'd probably use quadratic formula for this, but you're probably going to get decimal and need the calculator at the end. So x equals negative b, so negative 60, plus or minus the square root b squared minus 4ac all over 2 times a there. But we're going to use our calculator for this. Oh wait, that's not what I want. I want this. Well, we really want decimal anyway, so it doesn't really matter. One of the nice things about this, you can't do a plus or minus at the same time, but you could do plus square root. Square root is above the multiplication on this one. 60 squared minus 4 times negative 16 times 15. I'm going to stop right there for that part. Oh, let's do decimal. Hit the green button and enter. Now I'm going to divide it by negative 32. That's 2 times negative 16. Negative 32. So we're getting this number, x equals, oh wait, actually this is not the number that I want, because that is a negative number. So that does not make sense for the situation we're talking about, right? So instead, I should do the plus. So let's try it again. Negative 60 plus the square root of 60. Oh wait, you're right, I did do the plus. Let's do the minus. Oh, well, we're dividing by negative. It switches the sign, doesn't it? That's what's happening. Minus 4 times negative 16 times 15. So that gives me this number divided by negative 32. Okay, I got 3.98524. Okay, and this is in seconds. That's how long it takes to hit the ground. But what did the question ask me for? The velocity when we hit the ground. How would I find that? That's the derivative. So I would do h prime of 3.98524, which would just be, we found the derivative earlier, it's negative 32 times that number, 3.98524. Plus 60. And if we go over here and use our calculator for that, negative 32 times this number plus 60, we're going to get negative 67.528 if we round it to the nearest 3 decimal places, so negative 67.528. This would be feet per second. Why is it negative? It's going down. So velocity has direction. It's either up or down for that. You can imagine why this would be like important to know, because the speed with which you hit the ground could matter. So for example, if you are throwing something up in the air and it hits a person right here laying on the ground, whether or not it's going 2 feet per second or 67.528 feet per second is going to matter how much it hurts, right? If it's going faster, it's going to hurt more for that. So that's sort of an example that you might see. So your assignment is long, but it should be short. There are a lot of problems, but they should not take long, because you should be able to do them in just seconds for a lot of the first ones, because you're just using the power rule.